Hi everyone, welcome back to all of you on my YouTube channel. Here I am Ankit Mishra. I am teaching for Gate Chemical Experience from last 5 years. So I'm coming up with PYQ series. So here the next PYQ series in fluid mechanics is Laminar Flow. Already I have talked about lots of PYQ of different subject in all of these topics. So let's start with this question first. For the laminar flow of a shear thinning liquid in a pipe, if the volumetric flow rate is double than the pressure gradient. So when we talk about the laminar flow, the pressure drop per unit length can be written as Hagen-Poiseuille equation 32 mu u bar divided by dA square. Okay, and here you can see that volumetric flow rate is double. So when we talk about Q, so Q can be written as area of cross section multiplied with average velocity. So finally average velocity can be written as Q divided by cross sectional area, and that will be equals to 4Q divided by pi d square. Okay, so when we substitute this thing, delta P by L, that can be written as 32 mu, this is mu, and obviously that is 4Q divided by pi d4. Okay, so pressure drop is constant, but only volumetric flow rate is getting double. So here you can see that nothing is going to change, only volumetric flow rate is going to get change, right? So you can see here from Q is inversely proportional to, or sorry, the pressure gradient. You are supposed to write the pressure gradient. So from here you can see that delta P by L is directly proportional to mu into Q. So I can say delta P by L for 1 divided by delta P by L for 2, that is equals to obviously mu1 into Q1 divided by mu2 into Q2. Is that clear? So you can see that flow rate is getting double, right? So you are supposed to calculate delta P by L for 2 case, that will be equals to delta P by L into mu2 divided by mu1 and Q2 divided by Q1. So since this is getting double, right, so what will happen, it should be delta P by L of 2, that should be equals to 2 into delta P by L for 1 multiplied with mu2 by mu1. So if mu2 should be equal, if mu2 would be equals to mu1, then definitely mu2 by mu1, sorry, delta P by L should be equals to delta P by L 2 times. But here what is happening, shear thinning liquid is there, so mu2 will be less than mu1. So what will happen, this mu2 will be less than 2 times of delta P by L for first. Is that clear? So that's why from here your option B will be your correct answer. So all of these things you should know when you are solving this kind of problem, right? That is very, very important. And that's why this question put here, they put this question here to, you know, let you confuse and you can directly make answer is 2. That is wrong, right? Okay, now moving to the next question. Applying a pressure drop across capillary results in a volumetric flow rate Q under laminar condition. The flow rate for the same pressure drop in capillary of the same length but half of its radius. So when we talk about laminar flow condition, delta P by L, that is equals to 32 mu u bar divided by d square. Is that clear? So here you can see that pressure drop per unit length is directly proportional to, inversely proportional to okay, so again we can write that that is equals to 32 mu and u is equals to 4q divided by pi d square and divided by d square. So we can see that delta P by L is directly proportional to q divided by d4, right? So from here I can say that q is directly proportional to d4. So you can write q1 divided by q2, that is equals to d1 divided by d2 whole to the power 4, and finally you can say d2 will be equals to d1 divided by 2, that is given in the problem. So you can write q1 divided by q2, that is equals to 2 to the power 4. So q2 will be equals to q1 divided by 16, means the flow rate is getting decreased by 16 times, right? 1 by 16th of initial flow rate, right? So from here your question option D will be your correct answer. Okay, after that I'll move towards the next question, and the next question says that in a laminar flow through pipe of radius r, the fraction of total volumetric flow through a circular cross section of radius r by 2 centered at the pipe. So you are supposed to calculate volumetric flow rate here, ratio. So when the pipe radius is r, then how much volumetric flow rate is happening from here, this one, and when it becomes r by 2, right? So when this is r by 2 radius, right? So what is volumetric flow rate? So this will be your capital R by 2, this is R. So you are supposed to calculate, let's say this one is Q1, and in this case let's say this one is Q2. So you are supposed to calculate what is Q1 divided by Q2. Is that clear? Okay, great. So in order to solve this particular problem, let's say I'll go to a cross-sectional area element here. Something like that. We'll calculate differential volumetric flow rate first. Okay, so once we go and we'll calculate this differential area element here, this is R, and let's say this is your R plus dr, delta R technician. Okay, okay, so when we calculate dq, that can be written as integral, u dA. And what is dA here? dA is equals to 2 pi r dr. Is that clear? And what is ur? ur is equals to u max into 1 minus r divided by r whole square. So just calculate dq here. dq is equals to u is your obviously u max into 1 minus r divided by r whole square into 2 pi r dr. Is that clear? So dq can be written as, if I'll integrate 0 to q, so that can be written as 0 to r by 2. So obviously u max is constant, 2 pi is also constant, it will come out of the integral, and I can write 0 to r by 2 and r minus r q divided by r and obviously dr. So q can be written as 2 pi u max into, if I am going from 0 to r by 2, so that will be equals to r square by 2 minus, this is r square, so obviously r square divided by 4. Is that clear? Okay, so q can be written as 2 pi u max into, if I'll go from 0 to r by 2, so that will be equals to capital R square divided by 8 minus capital R square divided by 16. So from here you can write q is equals to 2 pi u max into 7 by 16 r square. Okay, for this one. And for this one, if I am calculating q, so for dq1 let's say this is dq2, so things will be very easy for you. For dq1 you can write 0 to r and obviously u max into 1 minus r by r whole square into 2 pi r dr, right? So dq1 that can be written as u max into 2 pi, it will get common, and you can write 0 to r minus r q by r square dr. So finally you can write q1 equals to 2 pi u max into r square by 2 minus r square r sorry, I think I have done some mistake here, so that will be equals to r4 by 4 r square, and once you'll substitute these things, so this will be your 64, right? Don't do any mistake here, that will be your 64. Okay, due to a space constraint, no, I have to sacrifice something here, right? So once you do the calculation you can write 7 by 64 r square into 2 pi u max. So finally you can write 7 divided by 32 r square pi u max. Okay, and from here you can write r4 divided by 4 r square and obviously 0 to r. So q1 can be written as 2 pi u max into, if I'll substitute r square by 2 minus, then you can write r square divided by 4. So finally you can write 2 pi u max into, if this is 4, so you can write 3 r square. So that can be written as pi u max into 3 by 2 r square. So when you calculate these things, q2 by q1, so you will be getting 7 by 32 divided by 3 by 2. So finally you will be getting sorry, this will be 1 only. I don't know why. 2 and 1, so that is 2. So finally once you will calculate these things, pi u max r square, this thing. So once you will substitute these things, you will be getting 1 by 2. So that will be q2 by q1, you will be getting is 1 by 16 only. That's it. Is that clear? So from here you can see your 7 by 16. I am really sorry for that. 7 by 16. From here your option B will be your correct answer. These questions were difficult, but again, if you will try in your exam, you can also solve, right? Okay. After that, I'll be moving towards the next question, and the next question says that two tank A and B of cross-sectional area 1 meter square each contain a fluid of density 1000 kg per meter cube, and the viscosity is given. The tank are connected by a pipe of diameter this, and the water height in the tank A is 6 meter and the water height in the tank B is 2 meter. Okay, and I'm just removing this thing so that I'll get a space for solving this question. Acceleration due to gravity is 10 meter per second x square. What is the average fluid velocity in the pipe as soon as the valve is opened? Okay, so you are supposed to calculate this thing. Okay, great. So let's say if I am assuming this one is my point 1 and this one is my point 2, so if I apply Bernoulli's equation, so I can write p1 by rho z plus v1 square by 2z plus z1, that is equals to p2 by rho z plus v2 square by 2z plus z2. Is that clear? Now since p1 minus p2 by rho z, if I want to calculate v1 square by 2z, v2 square by 2z will be 0 by, this is at a static condition, that will be equals to z2 minus z1. So I can write here p2 minus p1 divided by rho z, that is equals to z1 minus z2, that is equals to 4 meter. Okay, now once you calculate these things, now we can write the formula that delta p by l, that is equals to 32 mu u bar divided by d square, right? And delta p we have calculated 4, and the length of the pipe is given 1, that is equals to how much? Delta p is also you have to multiply rho into z divided by 1, that is equals to 32, and viscosity is given is 1, and u bar we don't know, and diameter of the pipe is given 0.02 whole square. So average velocity can be written as 4 into 10 to the power 4 into 0.02 whole square divided by 32. Is that clear? So from here you can see, so this will get cancelled out by I think 2. So u bar will be equals to half, which is equals to 0.5 meter per second. So finally you will get 0.5 meter per second, first case. Second, what is the total energy loss between the initial and final state? So when we talk about the total energy loss, so total energy loss can be written as m dot multiplied with g into hf, right? And what is hf? Hf is equals to delta p divided by rho z. And what is m dot? M dot is equals to rho into cross sectional area into average velocity. So once you will substitute these things, you can write rho into cross sectional area into average velocity into z into delta p divided by rho z. So z and g will get cancelled out. and yeah, rho and rho will get cancelled out. So power can be written as cross sectional area into U bar into delta P. So let's try to substitute these things. Pi by 4 into 0.02 whole square into average velocity is 0.5 into delta P. Delta P pressure drop is how much? 4 into 4 into 1000 into 10. So once you calculate 4 and 4 will get cancelled out. And from once you will calculate, you will be getting 4 into 10 to the power 4 joule from here. Okay, so with that I'll be moving towards the next question. This is really good question. This question says that a tube of diameter d and length L is initially filled with a liquid of density rho and viscosity mu. It is then pushed out by application of the constant force F to the plunger. So F constant force is applying on the plunger, and shown in the figure. Assuming laminar flow and pseudo steady state time required to expel the one half of the liquid. So if this is total half, that this will be equals to L by 2. How much liquid is getting expelled from here, right? So let's try to understand. Since this is based on the Bernoulli laminar flow condition, so we know delta P is equals to 32 mu U bar L divided by d square. And what is force? Force is equals to pressure into area, delta P into area. And what is area here? Area is the cross sectional area on which the force is being applied. So delta P can be written as pi by 4 into d square. Okay, and average velocity can be written as dl divided by dt. Okay, all of these things we have written. So now let's try to calculate F, that is equals to delta P 32 mu and dl by dt into L into divided by d square into area is pi by 4 d square. So this will get cancelled out, and again 4 into 8 it will get cancelled out. So finally force you will be getting 8 pi mu dl by dt into L. Once you get these things, now we are supposed to calculate the time. So I can write dt is equals to 8 pi mu divided by f integral L dl and L to L by 2, right? So if I'll integrate these things 0 to t, so t will be equals to 8 pi mu by f into obviously L square by 2, and once you substitute the limit L to L by 2, so you will be getting 8t equals to 8 pi mu divided by f into L square by 4 minus L square and multiplied with 1 by 2. So time will be equals to 3 L square by 4 into 1 by 2 into 8 pi mu divided by f, right? So once you'll cancel these things, so that will be equals to 3 pi mu L square divided by f. So the time required will be this one. Okay, so from here you can see 3 pi mu L square divided by f. So option A will be your correct answer. Okay, now moving to our next question. The question says that given a pipe of diameter d, the entrance length necessary for the fully developed laminar flow condition. So our laminar flow condition, full entrance length used to be 0.05 into d into Reynolds number NRE. So you can see that thermal entry length or entrance length is directly proportional to d into Reynolds number NRE. Is that clear? Okay, these things. Okay, now moving towards the next question again. The question says that two identical reservoirs open at the top and drain through the pipe attached to the bottom of the tank as shown in the figure. The two drains pipe are of the same length but of the different diameter. D1 is greater than D2. Assume the flow to be steady and laminar in both pipes, in both drain pipes. If the volumetric flow rate in the larger pipe is 16 times, so let's say here if it is Q1 and if volumetric flow rate is Q2, so Q1 is given as 16 times Q2, right? So means from here Q1 by Q2 ratio is given to you, that is 16. You are supposed to calculate the ratio d1 by d2. Okay, great. So when we talk about the velocity ratio here, v1 and v2, so height from here to here is same. So if you apply the Bernoulli equation, then you will get v1 equals to root 2 gh and v2 equals to root 2 gh, and h is same in both of these cases, so you will be getting v1 equals to v2. Is that clear? So what is q? Q will be equals to, let's say, q1 a1 into v1 and q2 equals to a2 into v2. Is that clear? So once you divide these things, you will get q1 by q2, that is equals to a1 by a2. Why? Because v1 and v2 is same. So I can write q1 by q2 is equals to d1 square divided by d2 square. Is that clear? And q1 is 16 times q2, so I can write 16 is equals to d1 by d2 whole square. So what will be the value of d1 by d2? That is equals to 4. So very simple question, but again one small tricks were required. One small trick was required to understand the solution. So option B will be your correct answer. Okay, now moving towards the next question. This question is also very important. The question says that a liquid is flowing through a pipe network. The length of the pipe section P, Q, R are shown in the figure. So all of these length is given L, L, L and L. Let's say the diameter of the section P and R is equal. So diameter here dP and dQ, dP equals to dr is given, dP equals to dr, and the diameter of pipe Q is twice that as. So if this is diameter Q, dQ, and this is ds, so I can say diameter of pipe Q is 2 times diameter of pipe S. That's it. The curvature effect is negligible. Then the ratio of volumetric flow rate in the pipe section is okay. Great. Since we are talking about laminar flow condition, so pressure drop would be same between pipe Q and S. Why? Because the length is same. So when two pipe is connected in parallel condition, the head loss or pressure drop will be same. So if I am writing P delta P for Q, that is equals to 32 mu UQ bar into LQ divided by DQ square. Is that clear? Okay. And if pressure drop is same and volumetric flow rate ratio you are supposed to calculate, right? Then the ratio of volumetric flow rate. Okay, so what is UQ bar? That is equals to QQ divided by area of Q. So I can write 4QQ divided by pi diameter whole square. Is that clear? And similar thing will be applied for the US, that is equals to 4QS divided by pi ds square as well. Okay, so from here we can say that delta P is directly proportional to Q divided by d4. Is that clear? So delta P will be constant, means Q will be directly proportional to d4, that is the laminar flow condition. So directly you can write QQ divided by QS, that is equals to dQ divided by ds all to the power 4. So since you can see that dQ by ds is 2, so you can directly write that flow rate in pipe Q divided by flow rate in pipe S, that will be equals to 16. That's it. The ratio will be 16 now. So from here your option A will be your correct answer. Okay, great. So after that I'll be moving towards this question. This question is also very important question. This is just based on the formula, and already I have done this question earlier. So you can say that what is the water is flowing under laminar condition in a pipe of length L. The diameter of the pipe is doubled for the constant volumetric flow rate. The pressure drop is. So I have told you directly delta P is directly proportional to d4. Delta P is inversely proportional to d4 if volumetric flow rate is same, right? So I can say that delta P1 divided by delta P2, that is equals to d2 divided by d1 all to the power 4. And if you are suppose diameter of the pipe is doubled, so d2 is 4d1, so I can write 2d1 delta P1 by delta P2, that is equals to 2 to the power 4, 16. So you can say that what is delta P2? Delta P2 is equals to delta P1 by 16, means pressure drop is getting reduced by 1 by 16th time. So decreases 16th time, right? Okay, now again I'll move about this question. This question is also very fundamental question, formula based. For the Newtonian fluid in the circular pipe steady state condition, in fully developed laminar flow condition, the fanning friction factor. So fanning friction factor used to be equals to 16 by Re, and Darcy friction factor is called as denoted as capital F, that is 4 into a small fanning friction factor F. So 4 into 16 divided by Re, that is 64 divided by Re. So you are supposed to remember this thing. This is very, very important, right? And very frequently you will get these things in your exam. Okay. I don't know why this is appearing here. I think this is from some another batches actually. Okay, so in this question you can see that consider a steady laminar fully developed flow in incompressible Newtonian fluid through two horizontal straight pipe 1 and 2 of a circular cross section. The volumetric flow rate in both the pipe are same. The volumetric flow rate, that Q1 is equals to Q2. So you have one pipe having volumetric flow rate is Q1, you have another pipe volumetric flow rate is Q2, and the volumetric flow rate in the pipe diameter twice is the diameter of the pipe 1. So D2 will be equals to 2 into D1. So all of these informations have been given to you. You are supposed to calculate the ratio of the shear stress at the wall of the pipe 1 to the shear stress to the wall of the pipe 2. You are supposed to calculate tau 1 by tau 2 at the wall of the pipe. So when I'll write tau 1, so tau will equals to minus obviously del p by del x, and length is same, and capital R by 2 at, since we are calculating at the wall of the pipe, right? And again, so I can write R1 by 2, and tau 2 will be equals to minus del p by del x into R2 by 2. So here you can see that pressure drop will be same, so this will get cancelled out. So finally I can say that tau 1 and tau 2 will be equals to direct R1 divided by R2, and from here you can say that R1 by R2 equals to 1 by 2. So I can say 1 by 2. The ratio of tau 1 and tau 2, that will be equals to 0.5. This is very simple. You can see only one or two step, you will be able to get the answer, right? So from here option A will be correct. But again you have to be very careful here that they are asking you to calculate the ratio of the shear stress at the wall of the pipe 1 to 2. So that's why I am calculating tau 1 divided by tau 2. Sometimes they will give you tau 2 divided by tau 1. So you have to check, and tau 2 divided by tau 1 will be equals to 2. So in option 2 is also there. So you have to be very careful which things which things have been asked from you. Just don't get anything wrong here. Okay, after that I'll be moving towards the next question, and I think this is the last question of laminar flow. And here you can see that the question says the viscosity of an incompressible Newtonian fluid is measured using a capillary tube of diameter 0.5 millimeter and the length. So let's say if you have a capillary tube something like that, and the length is given to you, length is equals to 1.5 meter, and the diameter of this pipe is given to you, that is 0.5 mm. The fluid flow in laminar steady state condition through the pipe. Flow rate is Q. Q is given to you 10 to the power minus 6 meter cube per second. The pressure drop across the length delta P is given to you 10 to the power 6 Pascal. So units are very, very important. You have to be very careful in the units when you are solving gate problem. You are supposed to calculate viscosity is given that in terms of some parameters. Let's say mu is given K into 10 to the power minus 3 Pascal second. You are supposed to calculate what is the value of K. So since this flow is happening in laminar condition, we can write delta P by L, that is equals to 32 mu u bar divided by d square. Is that clear? And the u bar formula, you know that you can write 4q divided by pi d square directly. So u bar can be written as 4 into q is 10 to the power minus 6 divided by pi into d square. D square is given to you 0.5 into 10 to the power minus 3 whole square. Is that clear? So directly u bar can be written as 4 into this is 0.5, right? So 4 by pi multiplied with that will be equals to again 4, that is equals to 16 by pi. U bar we have calculated. And what is delta P? Delta P is 10 to the power 6. Length of the pipe is how much? 1.5, that is equals to 32 into K into 10 to the power minus 3. And now I can write 16 divided by pi into how much? D square. So D square is given to you, that is your 0.5 into 10 to the power minus 3 whole square. Okay, So from here you can calculate the value of k, that will be equals to 10 to the power 6 into pi into 0.5 whole square into 10 to the power minus 6 divided by 1.5 into 32 into k, sorry, k you are supposed to calculate multiply with 16, something like that. Okay, so this will get cancelled out. Okay, so once you will calculate these things, you will be getting 1.02 value, right? The value of k from here. Okay, so with that I would like to end this lecture for the laminar flow condition in the pipe. I have solved lots of questions, and approximately you can see 15 questions have been asked in last 15 to 20 years. So that is a very important topic also. Every year one question is coming, or every alternate year one question is coming. So you can see the importance of this topic. Okay, so okay, see you in the next lecture where I'll be talking about turbulent flow in pipe. So not so much question is there from turbulent flow, very less questions are there. I think 7 to 8 6 questions are there only, and after that I'll start with the hydraulic pump. That is very important topic, and from here you will see approximately 20 25 questions are there. Okay, thank you.